Breaking laws of physics, JWST's Schrödinger's galaxy candidate shocks scientists. Astronomers armed with early data obtained by the James Webb Space Telescope, JWST, are hunting galaxies that existed just a few hundred million years after the Big Bang. It's been one of the JWST's main directives since its conception. But now, the JWST is leaving astronomers puzzled due to the Schrödinger's galaxy candidate. The candidate is so far away that it might break models of the early universe. And there's a catch. Rohan Naidu, an astrophysicist based at Harvard's and Smithsonian's jointly operated Center for Astrophysics, and his colleagues have been particularly good at uncovering these cosmic relics that have left the astronomer community bewildered. In July, after the JWST's first images were beamed across the planet, Naidu and his collaborators handed in a paper that resonated across the web, provoking a stir especially on social media. Using data from the JWST Space Observatory, researchers announced that they discovered a candidate for the most distant galaxy ever seen, and they dubbed it GLASS Z13. A new discovery is always welcome, but some new discoveries can be the demise of what we thought to be true. It seems we may be in the same situation with Schrödinger's galaxy candidate. You're about to find out why, plus a whole host of relevant data. Welcome back to Space Infinity. To initiate the journey, hit the like button, subscribe, and ring the notification bell. Why all the names? In his paper, released in early August, which is still undergoing peer review yet so far seemingly bona fide, Naidu and colleagues detailed another distant galaxy candidate. As one of the JWST's early release science programs, the galaxy candidate was labeled Sears 1749. It's an extremely bright galaxy that, if confirmed, would have existed just 220 million years after the Big Bang. There's a huge catch though. It could rewrite our understanding of the cosmos. The radiant galaxy is becoming quite popular and has already been given 3 different names. It was first known as GLASS Z13 and only lately became known as Sears 1749. Since the data suggests 2 potential locations for the illuminated galaxy, and no one is yet certain which one is accurate because further investigation and observations are still needed, astronomers also refer to it as Schrödinger's galaxy contender. Erwin Schrödinger was a Nobel Prize-winning Austrian-Irish physicist who developed a number of fundamental results in quantum theory until his death in 1961. It's safe to say that he first became famous for the Schrödinger equation, which provides a way to calculate the wave function of a system and how it changes dynamically in time. Schrödinger also wrote many works on various aspects of physics, statistical mechanics and thermodynamics, physics of dielectrics, color theory, electrodynamics, general relativity, and cosmology. He also constructed the imaginary experiment with the cat to demonstrate that simple misinterpretations of quantum theory can lead to absurd results which do not match the real world. It's called the paradox of Schrödinger's cat, where a confined feline trapped in a box of poison is both alive and dead until the box is opened, and the truth is actually confirmed. It demonstrates the most widely known example of a recurrent problem in quantum mechanics. Its dynamics seem to predict that macroscopic objects, like cats, can sometimes exist simultaneously in more than one completely distinct state. And this is the mix-up astronomers are currently having with Sears 1749. According to the paper, Schrödinger's galaxy contender could be one of the most distinct galaxies we've ever seen, or it could be standing by much closer to Mother Earth. Essentially, the data seems to indicate 2 possible places for the galaxy to be simultaneously, and we won't know which one is correct until we open the box check. That means we won't have a definite answer until a lot more observation is done and data is acquired. That's earned it the title of Schrödinger's galaxy candidate in the paper. Redshifts. So, how can a galaxy seem to be in 2 different places? So far, the guesswork points to the redshift. To determine how far away a galaxy lies, astronomers study wavelengths of light. Specifically, they're interested in a phenomenon of light known as redshift. In a nutshell, light waves leaving distant galaxies get stretched over time, shifting the waves down the electromagnetic spectrum and making them more crimson in color. So ultraviolet light leaving a galaxy like Schrödinger's won't reach Earth as ultraviolet light. Instead, it will be redshifted down into the infrared, which is great for our astronomer community because that's just the kind of light the JWST explores. Origins of redshift. Redshift has been a key concept for astronomers ever since the late 1800s, when it was discovered by Austrian mathematician Christian Andreas Doppler, who discovered that the frequency of sound waves changes if the source of sound and the observer are moving relative to each other. This is what happens to sound waves when a source of sound moves relative to an observer. This effect is called the Doppler effect. Mutually, the term redshift can be understood literally as the wavelength of light is stretched. This means the light is seen as shifted towards the red part of the spectrum. There are many everyday examples of the Doppler effect: the changing pitch of police and ambulance sirens, or train whistles and racing car engines as they pass by. In every case, there is an audible change in pitch as the source approaches and then passes an observer. Light also behaves in manners of waves. Light from a luminous object undergoes a Doppler-like shift if the source is moving relative to us. Ever since 1929, when Edwin Hubble discovered that the universe is actually expanding, humankind has known that most other galaxies are moving away from us. Light from these galaxies is shifted to longer or redder wavelengths. This is what we now call redshift. Since light travels at such a great speed relative to everyday phenomena, which is 1,000,000 times faster than sound, we do not experience this redshift in our daily lives. However, the redshift of a distant galaxy or quasar is easily measured by comparing its spectrum with a reference laboratory spectrum. Atomic emission and absorption lines occur at well-known wavelengths. By measuring the location of these lines in astronomical spectra, astronomers can determine the redshift of the receding sources. However, to be accurate, the redshifts observed in distant objects are not exactly due to the Doppler phenomenon, but are rather a result of the expansion of the universe. Looking at distinct wavelengths of infrared, the JWST has various filters. In examining a galaxy like Schrödinger, you can flick through the wavelengths like you might flick through a photo album. On the first few pages, fewer red wavelengths, you won't see a thing. Then, as you turn through and the wavelengths becoming redder, the ghost of a galaxy appears. In the most redshifted wavelengths, at the back of the album, the galaxy is a clearly defined object. Redshift measurements. Redshift, which is denoted by the parameter z and higher z values, means a farther distant object. One of the confirmed most distant galaxies discovered to date, GNZ11, has a z value of 11.09. In the case of Schrödinger, the research team claims that it could have a z value of around 17. That would mean this light is from a time some 13.6 billion years ago. This brings to light, pun intended, the reason scientists might have to rethink their models of how galaxies evolved in the earliest eras of the universe. You see, according to the main models we currently use to explain our cosmos, galaxies from that long ago should not be this bright. But astronomers and physicists aren't about to throw out the baby with the bathwater just yet. They figure they don't need to break physics just yet. They suggest there is good environmental evidence that Schrödinger's z value might be around 5, which would mean its light is about 12.5 billion years old. Other galaxies in the region around Schrödinger all lie at about this distance. It might even be that Schrödinger is a satellite galaxy of one of its more massive neighbors. The alternate hypothesis. Of course, Harvard astrophysicist Rohan Naidu and his colleagues aren't the only task force working on figuring out this cosmic puzzle. Another group of researchers is also studying this same exact galaxy with acute concentration. Georges Savala, an astrophysicist at ALMA, Japan, and his team added to the JWST data with data from Earth-based telescopes in the French Alps and Hawaii. They came to the conclusion that Schrödinger might be an imposter masquerading as a high redshift galaxy when it's actually a much closer, dusty galaxy undergoing rapid star formation. This group published their findings results to ARXIV. The main takeaway message: observations and investigations must continue to fully understand this perplexing galaxy candidate. JWST has been able to study the intensity of the light emitted by Schrödinger, but the astronomer community needs more measurements. In particular, spectroscopy will allow astrophysicists to scrutinize its redshift more accurately. Now it seems that aside from our state-of-the-art space instruments and tech only need time to study the supposed Schrödinger galaxy to solve the puzzle. Space is amazing, and it's imperative to gain as much knowledge about it as possible. Knowing the cosmos can help us understand more about ourselves. For this reason, hit that like button, subscribe, ring the notification bell, and share this video, because Space Infinity provides weekly videos of crucial space updates. Thanks for watching, and see you in the next journey through the depths of infinite space.